All right, folks, let's get into this. Number 10, Earth is sitting in a way too comfortable spot in space. In 1995, astronomers discovered the first exoplanet orbiting a sun like star, 51 Pegasi b. They expected to find something like Earth. Instead, they found a gas giant bigger than Jupiter, completing an orbit in just 4 days, basically slow roasting in its star's radiation. Picture yourself trying to exist on most planets we've discovered. You'd either be flash frozen into a cosmic popsicle or vaporized before you even hit the ground. Most of the universe operates on extremes: ice or fire, no in between. But Earth sits in what astronomers call the Goldilocks zone, the habitable zone around our sun where temperatures allow liquid water to exist. Not too hot, not too cold, just right. We're about 93 million miles from the sun. That's not just a random number someone pulled from a hat. And yes, if you drove at highway speed, it would take you 177 years to get there. Just in case you were planning a road trip, move us just 5% closer, and Earth becomes Venus, with surface temperatures hot enough to melt lead and clouds made of sulfuric acid. Shift us 5% farther out, and we become Mars, a frozen desert where any water is locked away as ice beneath the surface. Our orbital sweet spot is incredibly narrow, like threading a needle while blindfolded. But here's the thing: the more exoplanets we find, the more we realize how absurdly rare this setup actually is. Most planets orbit too close to dying stars, or they're in binary star systems where gravity yanks them around like cosmic pinballs, or they're wandering through space without any star at all. We found planets where it rains molten glass sideways, planets where the atmospheric pressure would crush you instantly, planets tidally locked so one side is always burning while the other freezes. And in all that cosmic chaos, Earth just sits here, stable orbit, circular, not wildly elliptical, the right distance from a star that burns at exactly the right temperature. What are the odds that a planet randomly ends up in this narrow band of space where life doesn't just survive, but thrives? Some scientists suggest that for every star that has a habitable zone planet, there might be 10,000 that don't. We essentially won a lottery where most people don't even get a ticket. Number 9. Earth has liquid water. Like an absurd amount of it. Mars has water. Europa has water. Even the moon has water trapped in shadowed craters. But here's the kicker: they have ice, frozen, inaccessible, locked away water that isn't doing anything for biology. Earth has oceans, plural, covering 71% of the planet's surface. If you flattened all of Earth's topography, the entire planet would be under a layer of water 2.5 miles deep. That's enough water to fill 1.3 billion trillion liters. To put that in perspective, if you tried to count every molecule of water on Earth, one per second, it would take you longer than the age of the universe. Twice over. I did the math. Well, scientists did, but I nodded along convincingly. Where imagine standing on the deck of a ship in the middle of the Pacific Ocean. No land in sight, just water in every direction extending past the horizon. You could sail for weeks and never see anything but blue. The Mariana Trench, the deepest part of our ocean, goes down nearly 7 miles. If you dropped Mount Everest in there, its peak would still be over a mile underwater. That's how much liquid water we're sitting on. But it's not just the quantity, it's that the water stays liquid. Earth's atmospheric pressure and temperature range keep water in all three states naturally: ice at the poles, liquid in the oceans and rivers, and vapor in the clouds. This cycling water is what drives weather, distributes heat, enables life. Without liquid water moving around the planet, Earth would be another dead rock. What makes this truly unsettling is how fragile that balance is. Water's liquid range is incredibly narrow in cosmic terms. Just 100 degrees Celsius separates frozen from boiling. In a universe that regularly operates at temperatures near absolute zero or millions of degrees, Earth threads this impossibly tiny needle perfectly. We maintain surface temperatures mostly between 0 and 40 degrees Celsius. That's the sweet spot. That's the range where chemistry can get interesting, where molecules can dance and interact and build something complex. And here's the horror movie twist: we almost didn't get water at all. Earth formed hot, molten, a ball of lava and rage. The water we have now came from somewhere else, delivered by asteroids and comets over millions of years. We got bombed by ice from space until we had oceans. The universe basically had to ship us the building blocks of life because we didn't come with them installed. What are the chances that enough water rich asteroids hit one planet to fill entire oceans, but not so many that they obliterated all life in the process? Every time you take a drink, you're consuming water that's older than the sun, water that traveled across the solar system and happened to land here in exactly the right amounts, at exactly the right time. The cosmic delivery system worked perfectly. Once. Number 8. Earth's atmosphere is basically life on easy mode. In 1952, London's Great Smog killed 12,000 people in 4 days. The air literally turned poisonous. Hospitals overflowed. People couldn't see their own feet walking down the street. And that was just a tiny change in atmospheric chemistry, a bit too much coal smoke mixing with fog. Now imagine what most planets are working with. The atmosphere of Venus is 96% carbon dioxide with clouds of sulfuric acid and temperatures exceeding 450 degrees Celsius. The atmosphere of Mars is 95% carbon dioxide, but so thin that it's basically vacuum. If you stood on Mars without a spacesuit, your blood would boil in seconds. Not from heat, from pressure. Fun stuff. Earth's atmosphere is different, almost suspiciously different. 78% nitrogen, 21% oxygen, 1% other gases, including argon and carbon dioxide. This mixture isn't just random, it's absurdly perfectly balanced for complex life. Oxygen is reactive, it wants to bond with everything. Too much oxygen in the atmosphere, and the entire planet becomes a fire hazard. Scientists estimate that if oxygen levels rose above 25%, even wet vegetation would spontaneously ignite. Forest fires would be unstoppable. Lightning strikes would cause continental scale infernos. Life as we know it couldn't exist. Too little oxygen, and you can't support complex organisms. Insects can't grow large without sufficient oxygen. Mammals can't function. Brains can't develop. Before oxygen levels rose about 2.4 billion years ago during the Great Oxidation Event, Earth was dominated by single celled organisms. Nothing complex, nothing interesting. It wasn't until oxygen hit the right levels that life exploded into the diversity we see today. But here's the thing that keeps atmospheric scientists up at night. Our atmosphere shouldn't be this way. Oxygen is so reactive it should have bonded with rocks and metals and disappeared from the atmosphere entirely. The only reason we have breathable air is because life itself, specifically photosynthetic organisms, continuously pumps oxygen into the atmosphere faster than it can disappear. Trees and plants and microscopic ocean algae are working 24/7 to maintain the atmospheric balance that allows them to exist. It's a feedback loop that borders on the impossible. Life creates the conditions that allow life to exist. Remove the trees and the oxygen starts dropping. Remove the oxygen and the trees can't survive. The whole system is self sustaining, but only because every piece remains in balance. And tip it too far in any direction and it collapses. And then there's atmospheric pressure. Earth's surface pressure is about 101 kilopascals. That's not just comfortable for humans, it's the pressure that keeps water liquid at Earth's temperature range. On Mars, where atmospheric pressure is less than 1% of Earth's, water can't stay liquid. It goes straight from ice to vapor. Earth's atmosphere is heavy enough to hold everything down, but not so heavy it crushes life. Another impossibly narrow window that we just happen to be sitting in. The strangest part, our atmosphere is see through. We can see the stars. Most planetary atmospheres are thick and opaque. Venus is wrapped in clouds so dense you'd never know the sun existed. Earth's atmosphere lets light through while still protecting us from harmful radiation. And it's a transparent shield that shouldn't work as well as it does. Next time you take a breath, remember you're inhaling a mixture that life spent billions of years creating, maintained by a planetary ecosystem that has to stay in perfect balance or everything dies. And it's worked without major catastrophic failure for hundreds of millions of years. The atmosphere isn't just perfect for life, life made it perfect. And somehow, against all odds, that's been sustainable. Number 7, Earth has an invisible shield that's constantly saving us. On March 13th, 1989, the entire province of Quebec lost power. 6 million people plunged into darkness. Hospitals switched to backup generators. Traffic lights went dead. The temperature was below freezing, and the cause wasn't a mechanical failure or human error. It was the sun. A massive solar storm, a coronal mass ejection, hit Earth's magnetic field and induced electrical currents in power lines strong enough to melt transformers. Quebec was down for 9 hours. Satellites tumbled out of orbit. Radio communications went haywire across half the planet. And here's the terrifying part: Earth's magnetic field actually protected us. Without it, that solar storm would have been extinction level. Earth has a magnetosphere, an invisible bubble of magnetic force generated by molten iron churning in the planet's outer core. This field extends about 370,000 miles into space on the side facing the sun and stretches into a tail millions of miles long on the opposite side. It's enormous, constantly active, and it's the only reason you're not dead from radiation poisoning right now. The sun doesn't just emit light, it constantly blasts charged particles into space at 1,000,000 miles per hour. Solar wind. This stream of radiation would strip away Earth's atmosphere, sterilize the surface, and make the planet uninhabitable. Mars used to have a magnetic field. Then its core cooled, the field collapsed, and the solar wind stripped Mars of most of its atmosphere. Now, Mars is a frozen desert where nothing survives on the surface. But Earth's core is still molten, still spinning, still generating a protective magnetic field that deflects 99% of the solar wind around the planet. Imagine standing behind a giant invisible shield while cosmic bullets spray past you on all sides. That's what the magnetosphere does, constantly, every second of every day. And you thought your immune system was working hard. Yet what makes this particularly disturbing is how fragile the system is. Earth's magnetic field isn't static, it fluctuates. It weakens and strengthens, and sometimes it flips completely. The north and south magnetic poles swap positions. This has happened hundreds of times throughout Earth's history. The last major flip was about 780,000 years ago. Scientists don't know exactly when the next one will happen, but geological evidence suggests we might be overdue. During a magnetic pole reversal, which can take thousands of years, the field weakens significantly, maybe drops to 10% of its normal strength. That means less protection from radiation, more solar particles hitting the atmosphere, higher cancer rates, damaged satellites, disrupted electronics, increased atmospheric loss. Life would survive, probably, but it wouldn't be pleasant. And yet, every previous flip happened without wiping out all complex life. Somehow, the ecosystem adapted. But that invisible shield? It's nothing compared to what's coming at number 3. Here's the kicker: most rocky planets don't have magnetic fields. Venus doesn't. Mars doesn't. Mercury has a weak one. Earth's magnetic field exists because our planet is large enough to maintain a molten iron core, because the core is spinning at just the right speed, because the temperature and pressure conditions deep underground are exactly right to sustain the dynamo effect that generates the field. Change any of those variables and the shield disappears. Some scientists even think the magnetic field might have been necessary for life to develop in the first place. Without it, right, the early Earth's atmosphere would have been stripped away before primitive organisms could evolve into something complex. The shield had to exist from the beginning, or we wouldn't be here. It gets worse. Cosmic rays, high energy particles from distant supernovas, and other cataclysmic events constantly bombard Earth. The magnetosphere deflects most of them too. Without it, cosmic rays would mutate DNA at rates that make evolution nearly impossible. Stable genetics require protection from space, and Earth's invisible shield provides that protection silently, reliably, for billions of years. We live inside a force field that's protecting us from threats we can't see, powered by process happening thousands of miles beneath our feet, in a layer of molten metal we've never directly observed. And if that system ever fails completely, and life on the surface ends. No exceptions. Number 6. Earth's gravity is balanced way, closer than it should be. There's a reason astronauts who return from space struggle to walk. After months at the ISS, their bodies forget what 9.8 meters per second squared feels like. Their muscles atrophy, their bones lose density. Coming back to Earth, feels like someone turned up the difficulty setting. Because in a way, that's exactly what happened. Gravity on the moon is about 16% of Earth's. Gravity on Jupiter is about 2.5 times Earth's. If you were standing on Jupiter, assuming you could find a solid surface to stand on, your body would weigh 2.5 times what it weighs now. Your bones would struggle to support you. Your heart would have to work overtime to pump blood against the increased force. And you'd collapse. Earth's gravity is 9.8 meters per second squared. That specific value, that exact amount of gravitational acceleration, is why life exists the way it does. And it's sitting in an absurdly narrow sweet spot. Increase Earth's gravity by 50%, not double, just 50%. Suddenly, the planet's atmosphere is thicker, heavier. The atmosphere compresses under its own weight. Oxygen becomes denser, but harder to distribute. Mountain ranges can't form as high because the increased gravity prevents rock from piling up. Flying becomes nearly impossible for birds. Large animals can't support their own weight. Evolution would favor smaller, stockier organisms. Complex life forms like humans wouldn't develop because bipedalism stops working when gravity gets too strong, or when walking upright becomes energetically too expensive. Decrease Earth's gravity by 50%. Now, the atmosphere is thinner. It escapes into space more easily. Atmospheric pressure drops. Water's liquid range shrinks. The planet can't hold on to lighter elements like hydrogen and helium. Volcanic activity decreases because magma moves differently under reduced gravity. The entire geological cycle that recycles nutrients and regulates climate becomes less efficient. Without enough gravity to sustain plate tectonics, the planet starts to die geologically. But here's the truly unsettling part: Earth's gravity is determined by its mass and radius. We have exactly the right amount of material packed into exactly the right size sphere to produce 9.8 meters per second squared. If Earth were slightly smaller with the same mass, gravity would be stronger. If we were slightly larger with the same mass, gravity would be weaker. The balance is precise, and it's not just about keeping us on the ground. Gravity holds the atmosphere in place. Too weak and atmospheric molecules reach escape velocity and drift into space. Too strong, and the atmosphere becomes oppressively thick. Gravity determines how water flows, how weather patterns form, how tides work. It influences everything from blood pressure to the size of insects to whether trees can grow tall enough to create forests. Some scientists even argue that Earth's specific gravity played a crucial role in human evolution. Bipedalism, walking on two legs, only makes sense in a gravity field like Earth's. Too strong, and we'd be quadrupeds, unable to spare the energy for walking upright. I'm too weak, and we'd probably have evolved to be tall and lanky with weaker bones and muscles. Our entire skeletal structure, our muscle mass, our cardiovascular system, everything evolved under this specific gravitational constant. What are the odds that a planet randomly forms with exactly the right mass and radius to create a gravity field perfectly suited for complex, intelligent life? You'd need enough mass to hold onto a thick atmosphere and generate a magnetic field through a molten core. You need the right radius so the surface gravity isn't crushing or negligible. You need the density of the planet's materials to be just right. And somehow Earth hit all those marks. The worst part? We don't fully understand why Earth has the mass it does. Planet formation is chaotic, out of dust and rocks smashed together over millions of years in a cosmic construction project with no blueprint. Most planets end up as gas giants, or tiny rocky worlds, or ice balls. Earth landed in the narrow range where rocky planets can support complex surface life, not by design, by accident. An accident so precise, it feels like someone was adjusting the settings. Number 5, Earth's surface stays active instead of turning dead. And boring Mars is dead, not dying, dead. Its volcanoes are extinct. Its core has cooled. There's no plate tectonics, no magnetic field, no geological recycling. The surface is a museum of ancient geology, frozen in time. Venus might have plate tectonics, but its surface is hidden under crushing atmospheric pressure and is occasionally resurfaced by planet wide volcanic eruptions. Mercury is a cratered wasteland. The moon is geologically dead. Earth is alive, constantly shifting, recycling, renewing itself. And that activity is the only reason we're here. And if you think that's disturbing, wait until you hear about the accident that happened 4.5 billion years ago at number 4. In 1960, geologists finally accepted the theory of plate tectonics. Earth's outer shell is broken into massive plates that float on the semi molten mantle beneath. These plates move, collide, slide under each other, pull apart. Continents drift, mountains rise, ocean floors spread, volcanoes erupt, earthquakes shake the ground. The entire surface is in constant motion, has been for billions of years, and shows no signs of stopping. Imagine trying to live on a planet where nothing moves. No volcanoes to release trapped gases back into the atmosphere. No tectonic recycling to bury carbon and regulate climate. No mountain building to create diverse habitats. Just a static crust, slowly eroding under wind and water with no renewal mechanism. Eventually, all the land masses would erode flat. The planet would become a uniform, boring sphere with no geological diversity. Life would stagnate. But here's the thing that makes Earth's geology truly bizarre. Plate tectonics requires a very specific set of conditions. You need a planet large enough to maintain a hot interior. You need water to lubricate the subduction zones where plates slide under each other. You need the crust to be the right thickness, not too thick to move and not too thin to maintain structural integrity. And you need all of this to remain stable for billions of years. Most rocky planets don't have plate tectonics. They're either too small and their cores have cooled, or they're too large and their crusts are too thick to break into mobile plates. Earth sits in a narrow window where plate tectonics is possible. And plate tectonics does something crucial. It regulates the planet's temperature. Carbon dioxide in the atmosphere creates a greenhouse effect, trapping heat. Too much CO2 and the planet overheats. Too little and it freezes. Plate tectonics acts as a thermostat. When the atmosphere gets too hot, increased rainfall pulls CO2 out of the air and deposits it on the ocean floor. Subduction zones pull that carbon into the mantle. Volcanoes then release some of it back into the atmosphere, but slowly over geological timescales. The system self regulates. Without plate tectonics, Earth would have gone the way of Venus, where a runaway greenhouse effect turned the planet into a hellscape, or Mars, where the lack of geological activity allowed the atmosphere to be stripped away. Earth's active geology kept the planet habitable for billions of years by continuously recycling materials and regulating climate. What makes this particularly unsettling is how fragile the system is. If Earth's water content were different, subduction zones might not work. If the planet were smaller, the interior would have cooled by now. If the crust were thicker, plates wouldn't be able to move. Everything has to be balanced perfectly for plate tectonics to function, and plate tectonics has to function for complex life to survive long term. And here's the horror movie twist. We don't fully understand why Earth's plate tectonics started in the first place, or why it's still going. Other planets with similar compositions don't have it. Venus is roughly Earth's size and should, theoretically, have plate tectonics. It doesn't. Something about Earth, some combination of factors we haven't fully identified, keeps the plates moving. And if they ever stop, the planet's climate regulation system collapses. The recycling ends. The surface slowly dies. Some scientists estimate that plate tectonics might have only another billion years left before Earth's interior cools enough for the system to shut down. When that happens, Earth becomes Mars. Dead geology, dying climate, the slow fade into cosmic irrelevance. But for now, the ground beneath your feet is moving, shifting, recycling, keeping the planet alive. And that activity, that constant geological churn, is the only reason the surface didn't turn into a lifeless wasteland billions of years ago. The ground is moving right now. Number 4. Earth's moon is quietly holding the planet together. On July 20th, 1969, Neil Armstrong stepped onto the moon's surface. One small step for man, one giant leap for mankind. But what Armstrong didn't mention, what most people don't realize, is that the moon isn't just a dead rock hanging in the sky. It's a stabilizer, a cosmic anchor, and without it, Earth would be uninhabitable. The moon is massive, about 1/80th the mass of Earth. That's enormous for a satellite. Most moons in the solar system are tiny compared to their parent planets. Mars has 2 moons that are basically captured asteroids. Jupiter has moons, but they're dwarfed by Jupiter's massive size. Earth's moon is proportionally huge, and that size is keeping us alive. Imagine Earth without the moon. The planet's axial tilt, currently about 23.5 degrees, would become wildly unstable. Computer simulations show that without the moon's gravitational influence, Earth's tilt could vary anywhere from 0 to 85 degrees over periods of millions of years. At 0 degrees, no axial tilt, there would be no seasons. The equator would roast while the poles froze. At 85 degrees, Earth would basically roll on its side. The poles would point at the sun for half the year, creating extreme temperature swings that would make complex life nearly impossible. The moon stabilizes Earth's tilt through gravitational interaction. It acts like a gyroscope in keeping the planet's rotation axis steady. This stability gives us predictable seasons, consistent climate patterns, and a stable environment for life to evolve over billions of years. Remove the moon and Earth becomes a chaotic spinning top, tilting unpredictably, creating environmental conditions that change too rapidly for ecosystems to adapt. But it gets worse. The moon also slows Earth's rotation through tidal friction. When Earth first formed, a day was only about 6 hours long. The planet was spinning much faster. Over billions of years, the moon's gravitational pull on Earth's oceans created tidal bulges. These bulges drag against Earth's rotation, gradually slowing it down. Without the moon, Earth would still be spinning at breakneck speeds. Faster rotation means stronger winds, more violent storms, shorter days, and less stable weather patterns. And then there are the tides themselves. The moon's gravity pulls on Earth's oceans, creating high and low tides that cycle twice a day. These tides aren't just about waves at the beach, they drive ocean currents, mix nutrients, create intertidal zones where some of the earliest complex life might have evolved. Without tides, ocean chemistry would be different. Nutrient distribution would change. Some scientists even think tides played a crucial role in the transition of life from water to land, providing a regularly flooded zone where organisms could adapt to both environments. Here's the kicker: the moon probably shouldn't exist. The leading theory for its formation is the giant impact hypothesis. About 4.5 billion years ago, a Mars sized object named Theia slammed into the early Earth. The collision was so violent it vaporized both the impactor and a chunk of Earth's outer layers. The debris coalesced into what became the moon. This is basically a cosmic car crash that, by sheer luck, created a satellite perfectly sized and positioned to stabilize Earth's environment. What are the odds? Most planets don't have large stabilizing moons. Mars has tiny moons. Venus has none. Mercury has none. Earth got hit by another planet in just the right way, at just the right angle, with just the right amount of energy to create a moon that's massive enough to stabilize axial tilt and regulate rotation, but not so massive that it disrupts orbits or causes tidal forces strong enough to rip the planet apart. Talk about threading the needle. The moon is also slowly drifting away from Earth, about 1.5 inches per year, about the rate your fingernails grow if you're keeping track. Billions of years from now, the moon will be too far away to have the same stabilizing effect. Earth's axial tilt will start to wobble. The protective influence that kept our planet habitable for billions of years will fade, but for now, the moon is right where it needs to be, doing exactly what needs to be done. The result of a violent collision that could have destroyed both objects, but instead created a cosmic partnership. Every time you look up at the moon, you're seeing the reason Earth has stable seasons, predictable climate, and a rotation rate compatible with life. It's a companion that keeps us balanced. And it's only there because of an astronomical accident that happened once. In one solar system, around one star, producing conditions that allowed intelligence to evolve. Remove the moon, and the story of life on Earth changes completely, probably ends early. Number three, Earth's chemistry actually encourages complex life. In 1953, Stanley Miller and Harold Urey conducted an experiment that changed how we think about the origin of life. They created a closed system that mimicked early Earth's atmosphere: water, methane, ammonia, and hydrogen. They zapped it with electricity to simulate lightning. Within a week, the mixture turned reddish brown. When they analyzed it, they found amino acids, the building blocks of proteins. Life's precursor chemicals formed spontaneously from simple ingredients and energy, which is cool, but also raises some questions. Because here's the thing: Earth's chemistry is specifically conducive to this process. And the more we learn about other planets, the more we realize how unusual that is. Life as we know it is built on carbon. Carbon atoms can form complex chains and rings, bonding with up to four other atoms simultaneously. This flexibility allows carbon to create the enormous variety of molecules necessary for biological complexity. Proteins, DNA, lipids, carbohydrates, all of them are carbon based. Carbon is the foundation of organic chemistry. Silicon can also form chains and bond with multiple atoms. Some scientists have speculated about silicon based life. Silicon oxygen bonds are too strong. Silicon compounds in oxygen rich environments tend to form stable crystals instead of dynamic molecules. Earth has abundant carbon and the right chemical environment to keep it reactive but not overly stable. We have carbon dioxide in the atmosphere, carbonates in rocks, carbon in the oceans. The carbon cycle moves carbon through different reservoirs, making it available for life. Increase Earth's carbon abundance too much, and you get a runaway greenhouse effect like Venus. Decrease it too much, and the planet freezes. Earth sits in a narrow range where carbon is plentiful enough to support massive biodiversity, but regulated enough to maintain stable temperatures. And then there's nitrogen. The atmosphere is 78% nitrogen, which is mostly inert and doesn't react easily. But certain bacteria can fix nitrogen, converting it into forms that plants can use. This nitrogen cycle is crucial for agriculture, for ecosystems, for protein synthesis. Without enough nitrogen, complex life can't build the proteins it needs. Without the right kind of bacteria to cycle nitrogen, it remains locked in the atmosphere, unusable. Phosphorus is another critical element. It's essential for DNA, RNA, and ATP, the molecule that stores and transfers energy in cells. Phosphorus is relatively rare in the universe, but Earth has accessible phosphorus deposits. Too much, and it would be toxic. Too little, and life couldn't store genetic information or power cellular processes. Earth's phosphorus levels are, again, balanced perfectly. What makes this particularly unsettling is that Earth's chemical composition is partly due to cosmic luck. When the solar system formed, heavier elements created in previous supernovas were present in the protoplanetary disk, where Earth accreted enough of these elements to create a chemically diverse planet. If the solar system had formed in a region of space with less heavy element abundance, Earth might have been chemically boring. Too much hydrogen and helium, not enough carbon and oxygen and nitrogen. Life as we know it wouldn't be possible. But here's the horror movie twist: Earth's chemistry isn't static. Volcanic activity releases gases that change atmospheric composition. Biological processes alter ocean chemistry. Plate tectonics bury and recycle elements. The entire planetary chemical system is dynamic, constantly adjusting. And yet, despite all this change, the overall balance has remained stable enough for life to thrive for billions of years. The system self regulates through feedback loops we don't fully understand. Whereas some scientists believe that life itself has shaped Earth's chemistry, the Gaia hypothesis suggests that living organisms regulate the planet's environment to maintain conditions favorable for life. Trees release oxygen, bacteria fix nitrogen, algae consume carbon dioxide. Life doesn't just adapt to the planet's chemistry, it actively participates in maintaining it. The whole system is interconnected in ways we're still discovering. And if any one element were missing or present in the wrong amounts, the entire structure collapses. Remove carbon, and there's no organic chemistry. Remove nitrogen, and proteins can't form. Remove phosphorus, and genetics stops working. The fact that Earth has all the right elements in all the right proportions available in forms that organisms can actually use is bordering on the miraculous, or at least statistically improbable enough to make you question how many times the universe had to roll the dice before getting a planet like this. So here's what I can't stop thinking about: what are the odds? Number two, Earth had time, stability, and way too many. Second chances the life on Earth has almost ended, multiple times. About 252 million years ago, the Permian Triassic extinction event wiped out 96% of all marine species and 70% of terrestrial vertebrate species. It's called the Great Dying. Volcanic eruptions in Siberia released massive amounts of carbon dioxide and sulfur. The climate destabilized. Ocean chemistry changed. Almost everything died, but life survived. The remaining 4% of species slowly repopulated the planet over millions of years, and eventually giving rise to the dinosaurs. Then, 66 million years ago, an asteroid 6 miles wide slammed into what is now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. The resulting shockwave, firestorms, and tsunamis were just the beginning. Dust and debris filled the atmosphere, blocking out the sun for years. Global temperatures plummeted, photosynthesis stopped, the food chain collapsed. 75% of all species, including the dinosaurs, went extinct, but life survived. Small mammals that could burrow and hide outlasted the catastrophe. When the dust settled, they emerged into a world without dominant predators. Mammals diversified, primates evolved. Eventually, humans appeared and started podcasts and YouTube channels, which may or may not count as proof of intelligence. Here's the thing that keeps paleontologists awake at night: Earth has experienced at least 5 major mass extinction events, and life bounced back every single time. Not just survived, bounced back, biodiversity recovered, evolution continued. The planet had enough time, enough stability, and enough resources to allow life multiple attempts to develop complexity. Most planets don't get this luxury. They're either too geologically dead to maintain stable climates long term, or they're too volatile with constant bombardments and environmental chaos that prevents life from ever getting a foothold. Earth has been around for 4.5 billion years. Life appeared about 3.8 billion years ago, almost as soon as the planet cooled enough to allow liquid water. And despite asteroid impacts, volcanic eruptions, ice ages, and atmospheric changes, life has persisted continuously for nearly 4 billion years. That's an absurd amount of stability, not perfect stability. Earth has been through hell multiple times, but the catastrophes were spaced out enough that life had time to recover between them. The planet provided second chances, third chances, fifth chances. Every time life got knocked down, the environment eventually stabilized just enough for it to crawl back up. And here's the kicker: complex, intelligent life took almost the entire history of the planet to develop. Single celled organisms dominated for billions of years. Multicellular life only appeared about 600 million years ago. Land animals emerged around 400 million years ago. And mammals diversified after the dinosaurs died out 66 million years ago. Humans evolved within the last few million years. If any of the mass extinctions had been slightly worse, if the recovery periods had been slightly shorter, if the environmental conditions had been slightly less stable, we wouldn't be here. Some scientists call this the rare Earth hypothesis: the idea that Earth like planets capable of supporting complex life might be extraordinarily rare. It's not enough to have liquid water and the right chemistry. You also need billions of years of relative stability with just the right amount of chaos to drive evolution without wiping everything out. You need a planet that can recover from catastrophes. You need time, and Earth had all of it. The sun is a stable star that doesn't fluctuate wildly in brightness. Jupiter's massive gravity deflects many asteroids that might otherwise hit Earth. The moon stabilizes Earth's rotation. Plate tectonics regulates climate. Magnetic field protects the atmosphere. Every system worked together to create a long lasting, stable environment, punctuated by brief periods of chaos that drove evolutionary innovation without causing total extinction. What are the chances that all these systems remained functional for billions of years? If Earth's history were compressed into 24 hours, humans appeared 4 seconds before midnight. What are the odds that none of the asteroid impacts were large enough to sterilize the planet completely? What are the odds that volcanic activity never went so far overboard that it turned Earth into Venus? Every single one of these near miss catastrophes could have ended the story early, but they didn't. Life got way too many second chances. And every time it came back stronger, more diverse, more complex. The fossil record shows this pattern repeating: extinction, recovery, diversification, extinction, recovery, diversification. It's almost like the planet itself is designed to test life, to push it to the brink, and then give it just enough breathing room to try again. But it's not design, it's luck. an uninterrupted streak of cosmic luck spanning billions of years. And the most unsettling part? We're still in that streak. The next mass extinction event could happen tomorrow or in a million years. But so far, the planet has been stable enough, protected enough, and resilient enough to keep the experiment going. Even life on Earth has had more opportunities to develop intelligence than most planets in the universe will ever get, and it used every single one of them. Keep watching, because number one is going to change how you see this planet forever. Number one, the more we learn, the less Earth feels like an accident. In 1961, astronomer Frank Drake wrote an equation attempting to estimate the number of communicative civilizations in the galaxy. The Drake equation considers factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, and the likelihood of life developing intelligence. Depending on the values you plug in, the equation predicts anywhere from 0 to millions of civilizations. But here's what we've learned in the decades since. Almost every variable in the Drake equation is more restrictive than we thought. We've discovered thousands of exoplanets. Most of them are nothing like Earth. Hot Jupiters orbiting too close to their stars. Ice giants far from any heat source. Super Earths with crushing gravity. Worlds tidally locked with one side always burning and the other freezing. Planets around unstable stars that flare unpredictably. Planets in systems so chaotic that stable orbits are impossible. And the few potentially habitable planets we've found. We don't know if they have atmospheres. We don't know if they have magnetic fields. We don't know if they have moons to stabilize their rotation. We don't know if they have plate tectonics. Every single one of those factors is critical for long term habitability, and Earth has all of them. The more we study planetary science, the more we realize that Earth isn't just sitting in the habitable zone. It's sitting at the center of a multidimensional sweet spot where dozens of independent variables all happen to align perfectly. The distance from the sun, the size of the planet, the composition of the core, the presence of a massive moon, the abundance of water, the right atmospheric mixture, plate tectonics, a stable star, protection from Jupiter, billions of years without total sterilization. Remember item number 7, the magnetic field protecting us? Item number 4, the moon stabilizing us? Item number 5, the plates recycling everything? None of these systems work in isolation. They're all connected, all dependent on each other, all perfectly balanced. Remove one, and the others start to fail. It's not 10 perfect accidents. It's one impossibly intricate machine made of 10 perfectly tuned parts. Change any one of these factors and you don't get Earth. You get Venus or Mars or something even less hospitable. The probability of all these variables aligning by chance is so low that some scientists have suggested we might be looking at a sample size of one. In the entire observable universe, Earth might be the only planet where everything lined up perfectly. But here's the thing that makes this truly existentially unsettling. We don't know if it's an accident or not. If you calculate the odds of Earth happening by pure chance, the numbers are staggering. The probability is so low that it borders on impossibility, and yet here we are. Either we got incredibly, impossibly lucky or there's something about the universe's initial conditions, the laws of physics, the distribution of matter, that makes Earth like planets more likely than the math suggests. Some scientists propose the anthropic principle. We observe a universe compatible with our existence because if it weren't, we wouldn't be here to observe it. It's a tautology, but it's also unsettling. Maybe there are infinite universes with different physical constants, and we happen to exist in the one where the constants allow for planets like Earth. Or maybe there's only one universe, and the constants are what they are for no reason at all. And we're the cosmic lottery winners. Others suggest that life might be inevitable given enough time and space. If there are trillions of planets in the universe, even a 1 in a trillion chance becomes likely somewhere. Our Earth could be that somewhere, the place where the dice rolled perfectly. Not because we're special, but because with enough trials, even the most improbable events become inevitable. But the deeper we dig into Earth's history and structure, the less it feels random. Every system is balanced. Every feedback loop regulates another system. Life creates atmospheric oxygen. Oxygen enables complex organisms. Complex organisms drive nutrient cycling. Nutrient cycling supports more life. Plate tectonics regulates climate. Climate influences biological evolution. Evolution shapes ecosystems. Ecosystems affect geology. It's all connected. It almost feels like the planet was fine tuned for intelligence to emerge, not by a designer, but by a cascade of fortunate circumstances that created a self regulating, self sustaining, and a stable environment for billions of years. Earth isn't just a rock orbiting a star, it's a system, a machine, a biosphere operating within narrow tolerances that just happen to be perfect for us. And the more exoplanets we discover, the more we realize how rare that perfection is. We're not finding many Earths, we're finding planets that fail in different ways: too hot, too cold, too massive, too small, no magnetic field, no atmosphere, unstable star, no moon, wrong chemistry, wrong distance, wrong everything. Maybe Earth is the exception, not the rule. Maybe in a galaxy of hundreds of billions of stars, there's only a handful of planets that got everything right. And maybe, just maybe, we're standing on the one planet in a trillion where all the pieces came together in exactly the right way, at exactly the right time, to create something capable of looking up at the stars and asking, are we alone? The more we learn, the more the answer feels like it might be yes. And that's not comforting. That's terrifying because it means Earth isn't just our home. It's the only home, the only place in the universe where everything worked, the only planet where the cosmic dice rolled perfectly, not once, but over and over for billions of years. An accident so precise, so impossibly well balanced that it feels like someone's watching, but probably no one is. We're just here, on a rock, floating through space, the beneficiaries of the universe's most improbable winning streak. And now that we know how rare this is, how fragile, how unrepeatable, it makes what we do next matter more than we ever imagined. Because if we're wrong, if Earth isn't rare, or if the universe is full of these accidents, then we're not special. We're just lucky. But if we're right, if this really is a one in a trillion planet, then we're standing on the only stage where the universe managed to wake up and look at itself. The only place where atoms arrange themselves into something that could understand atoms. The only rock that ever figured out it was a rock. And that means we're not just residents of Earth, we're the custodians of the universe's only successful experiment, the only witness to 13.8 billion years of cosmic history. No pressure. Thank you for watching and sticking till the end. If you want to see more videos exploring the strange and unsettling realities of space, hit that subscribe button. We've got plenty more cosmic nightmares coming your way. See you in the next one.